Hello everyone, welcome to another lecture of the course Digital Signal Processing. In the previous lecture, we have seen that the design of IR filters is completely based on the theory of analog filters. That is, we have an analog filter and in order to design a digital IR filter, we perform some kind of transformations that lead us to its equivalent digital digital IR filter. So in other words, the design of digital IR filters first step is basically designing of these analog filter. So what we can say is the first step to design digital IR filter is to design, or rather is designing its equivalent analog filter. So now we are going to start the designing of this digital IR filter by first considering the design of this analog filter. So let us start designing of the analog filter. Now various scientists proposed various models and circuits for different kinds of filters which had some pros and cons, and one such filter was proposed by Butterworth. So let us look at the Butterworth filters. So what Butterworth said is we can have a low pass filter whose magnitude response, that is in frequency domain, that is, let's say h of omega, follows the equation or the expression mod of h of omega square is equal to 1 upon 1 plus omega divided by omega c whole to the power 2n, where this n is basically order of the filter and this omega c is the cutoff frequency. And this h of omega is basically the Fourier transform of the impulse response. That is, suppose the impulse response is h of t, then its Fourier transform is given as h of omega, and if its Fourier transform follows the expression mod of h of omega square is equal to 1 upon 1 plus omega divided by omega c to the power 2n, then this h of t is basically a nth order low pass filter of cutoff frequency omega c. So now let us try to visualize this mod of h of omega c square expression for a particular value of omega c for different values of n. So let us consider this fc be equal to 800 Hz, and we know that omega c is basically equal to 2 pi fc, which is equal to around 5024 for this value of fc, and let us vary this n from 2 to 10 and let us see how it looks in the frequency domain. So let us plot this mod of h of omega square with respect to omega. So what we get is something like this. So this plot, this blue color plot, is basically for n equal to 2. This plot is for n equal to 4. This one is for n equal to 6. This one is for n equal to 8, and this green one is for n equal to 10. So what we can observe is this, for all the values of n, we have the frequency response which is similar to that of a typical low pass filter. That is, the lower frequencies, that is frequency which are lower to the cutoff frequency, which is around 5k, that is 5000. So less than that frequency, the frequency components are passed, whereas all the other frequency components are well attenuated. So this is the typical representation or plot for a low pass filter in the frequency domain. In our case, it is the magnitude square. So this is the representation for magnitude square. That is mod of h of omega square, which is plot versus omega for a low pass filter. Another thing that we observe is, as we increase the order, the attenuation in the pass band is reducing. That is, if we look at the plot for the n equal to 10 order, so we can see that till the cutoff frequency, the magnitude of the Fourier transform square is quite 1, which is constant, which is equal to 1, whereas for lower order it starts attenuating quite faster. So we saw that if the Fourier transform follows this expression, that is mod of h of omega square equal to 1 upon 1 plus omega divided by omega c to the power 2n, then we are guaranteed to get a low pass filter. So what we have is mod of h of omega square is equal to 1 divided by 1 plus omega divided by omega c to the power 2n. But now this is the expression for the magnitude square, and we want the expression for h of omega, that is the frequency response of h of t. Or we can also analyze this filter h of t in the Laplace domain. That is, we can analyze it in the Laplace domain expression given as h of s. So basically we need to either get the value of h of omega or h of s from the available expression. So let us start with whatever is available with us, that is mod of h of omega square is equal to 1 divided by 1 plus omega divided by omega c to the power 2n. Now this mod of h of omega square can be written as h of omega into h of omega conjugate. So this star simply represents the complex conjugate of this expression h of omega, and we know that h of omega can be calculated as integral from minus infinity to infinity h of t into e to the power minus j omega t dt, and if we take its complex conjugate, then what we have is h conjugate of omega is equal to integral from minus infinity to infinity h conjugate of t into e to the power j omega t dt. So what we have is h conjugate of omega is equal to integral from minus infinity to infinity h conjugate of t into e to the power j omega t dt. And if we consider real valued systems, that is for real valued systems, h conjugate of t is equal to h of t. So what we have is h conjugate of omega is equal to integral from minus infinity to infinity h of t into e to the power, we can write this as minus j into minus omega t dt. So this is equal to h of minus omega. So what we have is h conjugate of omega is equal to h of minus omega. Therefore this expression, that is mod of h of omega square, is equal to h of omega into h conjugate of omega is equal to h of omega into h of minus omega. So now what we have is mod of h of omega square is equal to h of omega into h of minus omega, which is equal to 1 upon 1 plus omega divided by omega c to the power 2n. Now let us try finding the value of h of s using this available expression. So now when we need to find the value of h of omega from h of s, what we do is we just substitute s equal to j omega. So now suppose we need to come back from h of omega to h of s, then we need to substitute this omega equal to s by j. So if we do this, then this term would be equal to h of s into h of minus s, which will be equal to 1 upon 1 plus s upon j omega c to the power 2n. So this leads to this expression, and by substituting s equal to s by j, we get h of s into h of minus s. Now this j is a constant term, so we can ignore it in the domain part. So what we have is h of s into h of minus s is equal to 1 divided by 1 plus s upon j omega c to the power 2n. So what we have is h of s into h of minus s is equal to 1 upon 1 plus s upon j omega c to the power 2n. And now using this, we need to find the expression for h of s. In order to find this h of s, let us analyze the denominator of this expression. That is, let us find the roots of this denominator. So for that, we need to equate this denominator to equal to 0. So by equating it to 0, what we get is s upon j omega c to the power 2n is equal to minus 1. Now we know that e to the power j plus minus pi is equal to minus 1. That is, this can be represented as cos of plus minus pi plus j times sine of plus minus pi. So this is equal to minus 1 plus j times 0, which is equal to minus 1. So for simplicity, let us consider it to be equal to e to the power j pi. Moreover, it is not only pi, it is pi, 3 pi, 5 pi, 7 pi and so on, that is odd multiples of pi. So what we have is pi into 2k plus 1. Now if we observe this expression, it is of the degree of 2n, that is it will be having 2n number of roots. So this value of k will be varying from 0, 1, 2 and so on up to 2n minus 1, and this will lead to 2n number of roots. So basically now we can replace this minus 1 as e to the power j pi into 2k plus 1, where this k varies from 0 to 2n minus 1. Therefore the value of s upon j omega c is equal to e to the power j pi into 2k plus 1 divided by 2n. Therefore s is equal to j omega c into e to the power j pi into 2k plus 1 divided by 2n. So what we have is s is equal to j omega c into e to the power j pi by 2 inside the bracket 2k plus 1 divided by n, and we can write this j. So this j can be replaced as e to the power j pi by 2, which is equal to cos pi by 2 plus j times sin pi by 2, which is equal to 0, plus j, which is equal to j. Therefore, the kth root of this expression, that is sk, will be given as omega c into e to the power j pi by 2 into e to the power j pi by 2 into 2k plus 1 divided by n. So what we have is sk is equal to omega c into e to the power j pi by 2 inside the bracket 2k plus 1 divided by n plus 1, which is equal to omega c into e to the power j pi by 2 inside the bracket 2k plus n plus 1 divided by n. So what we have is sk is equal to omega c into e to the power j pi by 2 inside the bracket 2k plus n plus 1 divided by n, where this k is equal to 0, 1, 2 and so on up to 2n minus 1. So basically this k, or rather sk, is kth root of denominator of h of s into h of minus s. So basically what we can do is we can write this h of s into h of minus s as 1 divided by s minus s0 into s minus s1 and so on up to s minus s2n minus 1, or rather we can write it as 1 divided by product of k from 0 to 2n minus 1 s minus sk. So this is the representation for h of s into h of minus s. Now this h of s would be having n number of roots, or rather n number of poles, and this h of minus s would be having n number of poles. So in totality they would be having 2n number of poles. Now we need to find what poles contribute to this h of s. So let us try understanding it with a simple example, in which what we'll do is we'll consider the value of n is equal to 3 and let this omega c be equal to 1, that is, let us consider the normalized value for the cutoff frequency. So in that case the roots, that is sk, would be given as omega c, that is 1 into e to the power j pi by 2. Inside the bracket what we have is 2k plus n plus 1 divided by n. So what we have is 2k plus 1 plus 3 divided by 3, which is equal to e to the power j pi by 3 inside the bracket k plus 2. And we know that this k varies from 0 to 2n minus 1, that is 0 to 2n, that is 6 minus 1, that is 5. So in that case we will be having 6 values. So let s0 will be equal to e to the power j pi by 3 into 0 plus 2, that is j 2 pi by 3, which is equal to minus 0.5 plus 0. J 0.866. Then s1 will be equal to e to the power j pi, which is equal to minus 1. s2 will be equal to e to the power j 4 pi by 3, which is equal to minus 0.5 minus j 0.866. Then s3 is equal to e to the power j 5 pi by 3, which is equal to 0.5 minus j 0.866. then S4 is equal to e to the power j 2 pi, which is equal to 1, and S5 is equal to e to the power j 7 pi by 3, which is equal to 0.5 plus j into 0.866. Now let us observe these poles, or rather these values, on the typical S-plane. Now if we observe, these are the roots of the denominator, so these are basically contributing to the poles, so we need to just represent it using a cross sign in the S-plane, so it can be represented as something like this. So if we observe carefully, all the 6 values lie on a circle of radius 1 and centered at 0. So basically this is the point, that is 0, 0, and the radius is 1. Moreover, if we observe, then this pole, it is 0, that is S0 is equal to minus 0.5 plus 0.866 j. This is S1, which is equal to minus 1. This is S2, which is equal to minus 0.5 minus j times 0.866. This is S4, which is equal to 0.5 minus j times 0.866. This is S5, which is equal to 1. This is this is S3, this is S4, and this is S5, which is equal to 0.5 plus j times 0.866. So these are the locations, 6 locations at which the poles are located, and out of these 6 poles we need to look at the poles that basically contribute to H of S. So now this is the typical S-plane, and this axis, that is this vertical line that passes through 0, 0, is basically the j omega axis. So this vertical line is basically the j omega axis, and we know that if the poles are located in the left hand plane, that is left side, that is towards the left of this j omega axis, then we can get a causal and stable system. It is not guaranteed, but we may get a causal and stable system. So in that case, what we can do is we can consider the poles that are located on the left hand side of this j omega axis. So if we look carefully, the poles that are located to the left of the j omega axis are S0, S1 and S2. That is, these are these 3 values, that is S0, S1 and S2. So let these be the poles of H of S. So if we vary this k from 0 to 2, or rather 0 to n minus 1, we are going to get the poles for the expression H of S. So the expression for H of S for this example can be written as 1 upon S minus S0 into S minus S1 into S minus S2. So this would simply give us the value of H of S. So what we have is H of S is equal to 1 upon S minus S0 into S minus S1 and so on up to S minus Sn minus 1. So this is equal to 1 divided by product of k running from 0 to n minus 1 S minus Sk, where this Sk, we know that it is given by omega c into e to the power j pi by 2. Inside the bracket we have 2k plus 1 plus n divided by n, and this k will be varying from 0 to n minus 1. So basically this expression that we have here is basically the low pass filter rather the Butterworth low pass filter of order n. And if we consider this omega c, so this omega c would be basically the cutoff frequency. So now let us look at the standard representations or standard polynomials for the denominator term, that is the denominator of this h of s, that is this product of k running from 0 to n minus 1 into s minus sk for some values of n, that is for some specific orders. That is the expressions for summation k running from 0 to n minus 1 s minus sk with omega c equal to 1, that is normalized cutoff frequency. So what we are going to look at is the denominator polynomial with normalized frequency. So if my order is 1, then the polynomial is given as s plus 1. If the order is 2, it is given by s square plus 1.414s plus 1. For third order, it is given as s plus 1 into s square plus s plus 1. For fourth, it is given as s square plus 0.766s plus 1 into s square plus 1.848s plus 1. For fifth order, it is given as s plus 1 into s square plus 0.618s plus 1 into s square plus 0.618s plus 1. For sixth order, it is given as s square plus 0.518s plus 1 into s square plus 1.414s plus 1 into s square plus 1.932s plus 1. For the seventh order, it is given as s plus 1 into s square plus 0.445s plus 1 into s square plus 1.247s plus 1 into s square plus 0.1082s plus 1. Now there is no need to remember or memorize these polynomials, as it can be easily found out by using this expression. That is, what we need to have is just find the roots, that is the value of sk, and simply multiply. So in this lecture, what we have seen is the Butterworth expression or the Butterworth approximation for a low pass filter of order n and cutoff frequency omega c. So suppose a frequency response h of omega satisfies the expression, that is mod of h of omega square is equal to 1 upon 1 plus omega by omega c to the power 2n, then we are guaranteed to get a low pass filter of order n with cutoff frequency omega c. And its equivalent in the Laplace domain can be given as h of s into h of minus s is equal to 1 divided by 1 plus s divided by j omega c to the power 2n. Now the poles of this expression are given by sk is equal to omega c into e to the power j pi by 2 into 2k plus 1 plus n by n, which is where this k varies from 0 to n minus 1. And therefore this h of s can be written as 1 divided by product of k running from 0 to n minus 1 s minus sk. Now this expression, that is h of s, is Butterworth low pass filter of order n, and the cutoff frequency would be this omega c. So in this lecture we discussed about the Butterworth filters. In the subsequent lecture we will see how to convert these analog filters into digital filter, that is convert the Laplace domain representation to its equivalent Z domain representation. Till then, let's stop here. Thank you.